Go. Hello and welcome back to Calculus 1, section 3.9 on derivatives of exponential and logarithmic functions. So we are going to take a look at a couple of formulas that will help you compute derivatives. This will be actually expanded on in Calc 2. There's going to be one chapter, but I believe only 2 or 3 sections on logarithmic and exponential stuff. But now we're going to learn the basic formulas, and then you guys are going to use that later on. Now, the part of this is also a very powerful way to take derivatives, and I always have a student who wants to be, the best and who wants to, stand out a crowd. So those students will actually learn and practice logarithmic differentiation so much that you can technically stop worrying about any other differentiation, and we'll see why and how. But for now, let's first focus on exponential function. So that would be y equal b to the x, b being any number, 2 or e. So far you have only seen the derivative of e to the x. But what if you have 2 to the x, 10 to the x, half to the x, right? So we can find derivatives of all of those, but let's first write all of the formulas we learned so far. So we learned that the derivative in respect to x of e to the x is just itself. That was the first formula we learned, I believe, in 3.3. Memorize that and that's it. Then we said, well, if we have this a in front, then it becomes a e to the ax, and this is the chain rule, right? Because you take the derivative of e to the x, you get e to the x. If it's ax, then this a drops in front. The goal for today is to do the derivative of b of x. And that's going to be derivative of b to the x is going to be b to the x times ln of b. So these are all of the formulas. Technically, this one over here is the general case for any base. And that includes base e. If you try to use this formula to compute the derivative of e to the x, you see that you are supposed to copy it and then times ln of e. But ln of e is 1, so it's just e to the x. It works for every problem, obviously. Now, almost every problem in calculus is going to be the middle formula, right, the chain rule one. Sometimes you're going to run into the top one, and almost never, right, run into the maybe 2 times. I don't know, just whatever. I have no clue why I erased this, but whatever. So this is what we have, and we have seen the use of this before. I'm just going to say let's have 2 raised to the, I don't know, well, let's start simple. The derivative of 2 to the x, and that's going to be copy 2 to the x and then times ln of 2. Very simple using that formula, right? What if you have the derivative of 2 to the sine x? You would say, well, obviously we use the chain rule because I have function composition. Yes, Very good. By the derivative, this stays the same. Multiply by the ln of 2, and then you have to multiply by the chain as well. So Control C, Control V, right? 2 to the sine x times ln of 2 times, and then the derivative of sine x is cosine x. So this all mess now, right, is the derivative. And yes, you can write this nicer, right? ln2 is the constant, so that goes in front. Then we usually put the exponential part, and then times the trig at the end. Again, there is nothing to simplify, nothing to factor. These all of these functions are, I mean, both of these functions are different. You have exponential, logarithmic, and a constant. So that's that. So in some sense, if you want the most general case, you look at the derivative of any base and any function. And that's going to be b to the f of x times ln b times the derivative of the function. Here. So that's the formula generalized for functions. So now your f of x could be just x, or could be sine x, could be another e to the x, could be literally x squared plus 1, like anything. Anything goes into that f of x, square root of x. And this particular formula covers any base b, so that can be any number, including fractions, including decimals, including e and pi and whatever. And then f of x can be any function. So now you can truly take the derivative of literally anything you come across. Now, for sciences, 99% of all of the models are expressed in the form e to the function, e to the x, let's say. And then that measly 1% is going to be the base 10. And you pretty much never see any other base in any of the applications. Almost never. Because they're really not important. They don't have... you can convert them into E and just use E all of the time. So that takes care of that part. So now we want to shift our focus to the star of this lecture, right? And the star is, oops, hold on. There we go. The star is what? Logs. Logs. Logarithm is learned for the first time, I think, in late algebra or even pre-calculus. Some students don't even see the logs before pre-calculus, which is the problem of education, obviously, the way it's set up. And then a lot of people are freaking out when they see logs. So the reason to have log is very simple. We can quickly see it from this example. 2 plus 3 is 5. 5 minus 2 is 3. 5 minus 3 is 2. 2 times 3 is 6. 6 divided by 3 is 2. 6 divided by 2 is 3. So you have addition and its opposite of subtraction to retrieve both of the input numbers. You have multiplication with its opposite of division to retrieve both of the input numbers. If I say 2 cubed equals 8, because 2 times 2 is 4 times 2 is 8, 2 cubed is 8, I can use the cube root of 8 to retrieve 2. And what is the operation which we have to use to retrieve 3? And that would be a log. Log base 2 of 8 is 3. So it belongs here with exponents. And also, we understand that the log is just a way to compute a number. Just like over here, you combine two numbers, anywhere over here, you combine two numbers to come up with a third number. Well, here it is, you combining two numbers to come up with a third number. So it follows all of the rules of your calculations before, where you calculated using two numbers, you calculate the third number. It's just that you are not used to this operation, so obviously, right, you shut down and say, like, well, I have the other ones. Where this one is doing something unique that others can't, so we have to add it to the list of our basic computation. Now, I don't know, people discriminate against it, I guess, because it uses letters rather than a cute symbol, right? Over here you have plus and minus and multiplication, division, then these visual cubes and cube roots and so on. And log is the only one that has letters, right? Maybe if that one had a cute symbol, maybe we should, you know, have a convention of all mathematicians in the world and just say 2 heart 8 equals 3, and all of a sudden logs are not going to be a problem for anyone. I don't know, maybe. Or 8 heart 2. 8 with a base 2 log. Whatever. Notation, you know, maybe if we have a cute symbol. But as you can see, logs are nothing special. Nothing special. It's just a way to compute a number given two numbers. And log is not a function, because addition is not a function, multiplication is not a function, it's a computation. You make a logarithmic function when you involve variables, like x, let's say, and y, and when you put them in a form that you have a function. So the same like 2 plus 3 equals 5 is a computation. If you say x plus 3 and you put y in front, then this is a function and becomes a linear line through 3. If you go 2 units away, this point would be at 5. So the one way is a computation and the other way is a function, but you must have a variable for it to become a function. Same thing, 2 times 3 is 6. 2x, y equal 2x is a function. 2 times 3 is not a function. So log base 2 of 8 equals 3 is not a function. It's a computation, like anything else. You can use the calculator if you don't know how to compute it by hand. You use the calculator to compute that 3. Now, can we make it into a function? Yeah, but you have to have log base 2 of x. So I found throughout the years that a lot of students are only associating logs to functions. They do not associate logs to its basic existence, which is computation. Same thing, guys, happens for your trig. Trig, when you say sine of theta equals opposite over hypotenuse, that's not a function. That's computation, because you are saying that sine of 30 degrees, actually pi over 6, is equal to 1/2. There's no function here. Sine is not a function. Sine is a computation. It's an operation that you apply to pi over 6 to get a number half. It's like a conversion from angle to a number. You can think of it that way. And the meaning of it is the opposite and the hypotenuse have 1:2 ratio. That's all it means. There's no function there. It becomes a function when you write y equals sine x. Now is a function because you are allowed to stuff a number in there and it's not defined. But when you put sine pi over 6, that's a number. It's a half, right? So the same thing goes with logs. Logs are just a computation to figure out and get this 3. If I plug in an x, then it becomes logarithmic function, and then that logarithmic function has its specifications, which is what you learned in your pre-calculus course. So you learned maybe the graph of the logarithmic function goes through 1, and you can use that graph to calculate the value, right? That the log of any base of 1 is equal to 0. And if you use the conversion into exponential, you would have a to the 0 equals 1, which you know it's true, right? 3 to the 0 is 1, 10 to the 0 is 1. So you would have this particular conversion there, but you can use the graph. Then you have your vertical asymptote over here at x equal to 0. You have your domain, right, which is 0 to infinity. You have your range, negative infinity to positive infinity. You have your x-intercept at 1, 0. So all of the specs that you learned about the function, they only apply if you have an x over here. They do not apply here because none of these things apply to number 8. Oh, sorry, number 3. Number 3 is a number on the number line. Number 3 is just 0, 1, 2, 3. That's it. There are no asymptotes there. There is nothing, right? So log 2 of 8 is 3. Log 2 of 8 is constant. It's 3. So you can put it as a point, or you can put it as a horizontal line through 3, depending on which concept you are talking about. But it's a number, right? Where log x is a function. And we want to learn as much as possible about log x as a function because, again, it's used in sciences. Those of you in chemical engineering and chemists, you will be computing the pH values, right? That's going to be log base 10 will have in it. So if you can calculate the change in pH values, right? Which will obviously be some kind of derivative of that log function, because anytime you say change, immediately that means, as soon as you say change, it immediately means derivative. So now we are going to take a look at the logarithmic and then a few other things that we need to know about the log. Log of base e of x has the shorter notation as ln x. So ln x is not a new concept of a log or something. It's still the same log function as before, except it's a very special base e. And the log of base 10 of x is just log x. We don't write the 10. These are the only two that you actually use in sciences. You are not going to find a formula with base 7 or 13 or anything like that. All of your bases in science will either be e or rarely base 10. So let's say, waves, if you're talking to sine intensity, earthquakes, whole bunch of stuff, they do have log base 10. But for electrical engineering, you are going to charge and discharge battery with E. You are going to have we've seen the oscillation for physics, right? Had e to the negative at. So it's pretty much going to be ln, right? And then, because it's all base e, and then sometimes when it's base 10, it's going to be log x. So when you go to your calculator, right, you have the capital ln button to compute ln's, and you have the log button that computes base 10. So those are just notation shortcuts. They all still belong to the good old log a of x, right? Where a is maybe 2, maybe e, maybe 10, right? Depends on what you're observing. But for sciences, right, you have this, and you would know that the calculators only have these two buttons. So the more sophisticated calculator is, less ln buttons will have. So basically, the lowest level calculators, right, are the ones that actually allow you to type in any base, because you actually don't need that. Sciences do not use any other bases than E and 10, and then you will find that the highest level of calculators only have one of these two, primarily ln. And a lot of the software and so on will only have one of them. So the highest level of this will only have one of them, because we also have a change of base formula that can convert any log of any base to any of the two. So if you have change of base, this is like all of your pre-calculus log stuff mushed into a 10-minute review. Change of base, so log any base of any number can be computed as ln b divided by ln a, or log b divided by log a. That means you are using one of the two buttons on a calculator. This is the reason why calculators, like a serious calculators, the higher end calculators, do not have log a, b, where you can plug in any numbers, because they are expecting you to know the change of base formula, and also they're not expecting you to run into a log 2 of 8, right? Because sciences, as I said, generally don't have that in any of the formulas for engineering and chemical stuff and medical engineering and computer engineering. Like, none of them have log base 3 or log base. It's not there. Nature doesn't work through log 3, base 3. Now, there are 3 formulas which you will have to memorize if you haven't memorized those before, because we are going to need those for our logarithmic differentiation. And those 3 formulas are log a of xy is log a x plus log a y. Then you have log a x over y is log a x minus log a y. And finally, log a of x to some power p is p log a x. If you don't know these formulas, if you don't remember them from pre-calc 1, you have to learn them now. My hope is that you know these basic formulas from pre-calc, because these types of formulas you are supposed to compute in your head when you see logarithmic differentiation, because logarithmic differentiation is something that you do in calculus. Breaking those formulas using this is something that should be mental math. Like you don't write down 3 plus 2 equals 5 and then you move to the next step, right? This is something that happens in the background of your head, right? In subconscious mind. All of these should be in your subconscious mind to get through the calculations. That's it. That's our story of logs, and understanding that log is calculation, just an operation to compute numbers. And then if you plug in x, it becomes function with all of the properties and features. And then we have shorter way to compute those, to write those that are always used. So ln x for natural log for base e, and for base 10 we just don't write the base at all. In either case, you are just saving writing 2 characters. That's actually what it is, right? And you have the change of base to convert anything you see into this form, and then these 3 formulas that you need, as well as, right, that you need for what it's coming up. Now let's take a look at some of these basic derivatives of what you are supposed to know as you are taking derivatives of ln functions. So if you have a derivative, right, if you have the ln function, let's say ln x, and you want to take the derivative of ln x, so the derivative of ln x, that's going to give you 1 over x. So this is your introductory formula. Here and there you are going to have ln x, but most of the time you are going to have the derivative of ln of some function of x. And this is the one that you absolutely must know or you're done, technically, right? You won't be able to do any of the ln problems. And it's so simple. It's f prime over f. Whatever this function is, you just take, you do Control C, Control V, you copy the function as is, and then you put its derivative upstairs. That's it. There shouldn't be thinking about this. You should just do, right? So this is your equation for ln. Let's put the sparkle on it. There we go. So now, how do you use this? Not a problem at all, I hope. The derivative of ln of x squared plus 1 is, what do we say? Control C, Control V, put its derivative on top. Move along. That's all it is. The derivative of ln of tangent x, let's say. Control C, Control V, the derivative of tangent is secant squared. Move along. You say, wait, we can simplify. Yes, we can, right? That's the simplifying part. To do the calculus is as simple as Control C, Control V, take the derivative of whatever you see in the denominator, take the derivative on top. Now, can we stuff a product rule and a chain rule? And yes, we can stuff all of that in it. But when you learn the theorem, when you learn the form, then you will be able to recognize, oh, there's a product rule which I still have to work in, right? Why not? Let's have an example. So say you have ln of x squared e to the x. Why not? Now, Control C, Control V. The derivative of this on top is a product. So you have to use the product rule. Copy the first, derivative of the second, plus copy the second, derivative of the first. And if you simplify this, you can kick out x e to the x, which leaves you with x plus 2, divided by x squared e to the x. Now we see that e to the x and e to the x cancels, and x cancels the square, and you get the problem as x plus 2 over x. I am just hoping that you are going, what the hell, where did the e to the x go? Like, how is it possible to get a derivative that has e to the x in it, and you have no e to the x at the end? Yeah, because remember the formula, ln x squared plus ln e to the x. So this becomes 2 ln x plus x. See? No e to the x, actually. If you use basic algebra, those formulas that I wrote in red, and I said if you don't know this, you are technically doomed. Well, you are, right? Using that formula and applying that basic formula on this, it eliminates, I'll put algebra, it eliminates from the derivative e to the x completely, and this becomes 2 1 over x plus 1. And if you find the common denominator of x, that's 2 over x plus x over x, which is x plus 2 over x. See? So sometimes it's possible to eliminate. And also, if I use those formulas, right, these formulas, you see that I eliminated also the product rule, which is going to take the central stage. If you know logarithmic differentiation, you never have to do product and quotient rule again. Now, you still need the product rule formula because we are going to have one of the most powerful integration techniques in Calc 2 called integration by parts. That's going to be built off of the product rule formula. Product rule will also appear in differential equations for integrating factor calculation. So you cannot say, oh, I can replace my product rule with this and just never know it again, because future courses will have the product rule. But in the essence, you can forget the product rule forever because it is no longer needed. This calculation, when you break the ln, is right with the ln formula, is breaking the product rule into basic addition, and you see that we are getting the same solution, where over here I used algebra to break the problem, and then I took the derivative, and over here I didn't use the algebra, I used the product rule. It doesn't matter, right? We got it either way. Now you might wonder, well, yeah, that's good when you have ln, but if I just have a problem without ln, can I do it then? And the answer is yes. That's exactly what is going to be called logarithmic differentiation. You're going to put logs on purpose to eliminate the rest of the annoying stuff. Now we need to get there. So let's first practice this a little bit more. We have our formula here, and this is the formula that you will be dragging throughout your Calc 2, Calc 3 differential equations. This formula never goes away because ln derivatives are very frequent. Most of our science stuff is dealt through models that have e to the x, therefore they will have ln x as well. And they're rarely going to be ln x, it's going to be ln of a function, right? When you have only ln x, then it's just the formula on top. But when you have a function there, which is mostly the case, you will have to deal with the f prime divided by f. The sooner you learn it, the better your Calc 2, 3 differential equations will go. All right, let's take a look at a general case, which is literally never used, but we do have to write it down, which is the derivative of any base, log of any base of any function. So this is as general as you can make it, because in this particular case, right, as general as you can make it, in this particular case, you are going to have the base. Now, I am quickly scanning through to see, yes, okay, good. So this will be, again, the same deal. The derivative divided by the original function, and you're just adding ln b on the bottom. So that's the general case. But as I said, you are not going to take a 400 level course in a STEM field. I don't care if you're taking chemistry, mechanical engineering, electrical. You're not going to find log base 3 of sine x and then you have to use this. That's never going to happen. None of them will be log base 3. They will either be 10 or e base. So that's why I said this. For the sake of your future education in those higher courses plus Calc 2, 3, and IFIQ, this sparkly equation is what you need to know at all times. But the general case does exist, and it still has that extra ln b to make up for the fact that this thing over here is not e. If it is e, ln of e is 1. It collapses to the sparkly equation up there. So that's that. I'm going to just flip into the homework over here and say that only 2 problems, 3, 4. 4 problems have ln log with a base other than e or 10. The rest are all base e or base 10. Okay, so what should we do? Let's do the problem 68 is log of a log. And this is one of those log base 2. Log base 2 of log base 2 of x. Again, this is completely pointless from any perspective for like a applied thing in a lab or a job. This is mostly like, look, ma, what I can do, right? So we're trying to find the derivative of this. I have a chain rule here. I have a log stuck inside of a log. So the derivative of log is copy the inner function as is. That's the inner function copied. And then multiply by the ln of the base. And then put the derivative of the function you copied on top. Now the derivative of this is going to be 1 over x times ln2 on the bottom as well. Because, right, it's not ln x to be just 1 over x. It is log base 2 of x, which means it's 1 over x and then ln2 in there. And now we simplify this as much as possible. We have a double fraction, so you can put over 1, multiply 2 that are far apart. So that's going to give us 1 on top. And then in the denominator, I have ln2 squared, because I have ln2 times ln2, right? You multiply 2 that are close by and multiply 2 that are far apart. So ln2 times ln2 is ln2 squared. You can actually write that nicer as ln squared of 2. That's the simpler way to write with less parentheses and mess. Then you have the x, so all of that times x, and all of that times log 2 of x. And that would be the derivative of the upper one. All right, we have to do the next one. So 69. This one has a really good point to make. 3x plus 1 to the fourth power. Tell me what you see in this problem here.
There are two separate chain rules?
Yeah, nice. Very good. This is technically ln of x to the fourth, right? X to the fourth. So there will be a function inside ln, which is a chain rule. But then this is not x. This is 3x plus 1, which makes it a double chain rule, as you said. Very, very good. Now, you can go in as a double chain rule, or I'll write it in blood over here. We know the log formulas. The power rule says you can kick this in front of the log. So this problem now becomes 4 ln of 3x plus 1, and you just, using the basic algebra, you eliminated a chain rule. And that is a huge time saver, right? In terms of steps and paper and ink and everything else, right? Now, when you want to take the derivative, you copy the 4 because it's just a constant. And you are dealing with the derivative of this, which is Control C, Control V. And then the derivative of that is 3. So altogether is 12 over 3x plus 1. It is really quick when you know those three formulas and they just completely erase your product rules and chain rules and quotient rules and all of those things. They are just, just gone, which is really, really cool. Learn those formulas. So from here to here, used log or ln, whatever, ln of x to the p is p ln x. So that formula literally killed the whole chain rule. And it's the basic algebra formula for logs. So that was a really good problem. And then we immediately go into problem 70, which I am going to ask you to try and power through. So here we go. I'm leaving you with ln of 2x divided by x squared plus 1 cubed. So this should be a living nightmare to do it. Like straight up do it.
Do you mean nightmare in general, or nightmare if you just don't use the log rules?
Nightmare if you don't use the log rules. If you use the log rules, it's a joke. If you do not use algebra log rules, it's a nightmare. You do see, right? You do see the
Yeah,
chain
I
rule
do see
inside,
it.
yeah, right? You
I see
see
it.
a chain rule inside the quotient, and then that quotient inside the chain of ln, right? So it's a living nightmare to do it. But if you use those formulas, it turns into a joke. So using the pre-calc, right? I'm just going to write the breakdown of this. It's the derivative of ln of 2x plus, well, actually, plus 3 ln of x squared plus 1. So I hope you had this immediately. This is just using the formulas. Why did I say plus? It's a minus.
Yeah, that's what I
Yeah,
was gonna say.
minus.
All right, cool. Minus. Yeah. So we have, this is the top, then minus, this is the bottom, and here is that 3 that was the exponent that jumps outside. So that's our life right there. And now taking the derivative is a joke. You have immediately, as soon as you see ln, it's a fraction. You copy the function as is and the derivative on top. Minus 3 times, it's a constant, just copy it. Oh, there's ln. Derivative, the function as is on the bottom, its derivative on top. So I have 1 over x minus 6x over x squared plus 1. It's a really quick calculation. You do not want to run this as a quotient and chain and all of that stuff. I'm going to write it and then erase it. If you go and you say, without using those formulas, it can be done. But, yeah, what do we get? We get it's ln, so copy the function as is, and then take its derivative on top. Well, that derivative is a quotient rule, so you have your x squared plus 1 to the 6th power, then copy x squared plus 1 to the 3rd times derivative of the top, minus copy the top, and then derivative of the bottom, which is another chain rule. So 3x squared plus 1 squared times the derivative of the inside. Like, really? Are we gonna go there? When it's so simple to learn the 3 formulas from pre-calculus or algebra, whatever you learned it, and solve this problem in 2 steps. Look at this mess that you now have to simplify into this. Believe it or not, this simplifies there. Now, good luck, right? So we want to learn those formulas. I'm just gonna get this monstrosity off the screen. We learn those formulas to make a joke out of these problems. That's what those 3 formulas do. And now we finally reach that state where you learn logarithmic differentiation. It is very important technique. See, every problem we had so far had ln in it, or a log of some kind. So you use those formulas. Now, the logarithmic differentiation is going to ask you to solve the derivative of, let's say, x squared cosine x divided by 4th root of x squared plus 6x minus 3. There's no ln in it. And at this point, right, if you already didn't break your screen saying, really, right? At this point, you say, well, great, I have a quotient rule for the whole problem. Then I have a product rule on top, and I have another chain rule on the bottom. So this is going to take, 15 years to go through. Simplifying it is just going to be a living nightmare. And I'm going to claim that if you learn logarithmic differentiation, you can take the derivative of this in factored form mentally without writing anything down. If you know logarithmic differentiation, any derivative that we had so far in chapter 3, you can, with practice, you can do mentally without writing anything down. I don't care the amount of product rule and chain rule and everything else. You will just go here and you would look at this and you would say, oh, well, this is simple, because all I need to do is, blah, 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 and you just write the answer in one shot. So now, what is the answer for something like this without doing any work? You just look at the problem and you write the factored form of the solution. You copy the problem as is. That's always the first step. And then that will be multiplied in certain terms, right? So this is going to be 2 over x plus tangent x minus, well, not 1/4, 4, and then you'll have your squared plus 6x minus 3, and over here, oh, sorry, that's a 2. I messed up. I haven't done this in a couple of months, so I messed up. Here it is. This is your, there's no x here. So this is the derivative of this mess done mentally without writing any steps. And believe me, I haven't done any of the product rule, quotient rule, chain rule, anything, even though they were all on a pile.
Would you accept something like that on the test, or would you want us to do the steps out?
Well, I'm going to show the steps, and obviously you can plug this into the software and get this form out, right? So all of the steps need to be there for your partial credit, full credit, and then if something is wrong, you don't have the steps, then it's 0 for the entire, 10 points problem immediately. So the steps are very beneficial, but what I wanted to demonstrate here is that if you practice what I'm going to teach you now enough, you should be able to solve every derivative that we had up to now in the entire chapter just by looking at it without writing anything down. So let's take a look at the procedure on a problem that has less of these things, and then go from there. So let's first work and learn the procedure on the problem that has less writing. So I'm just going to have, let's say, x to the 4th times, I don't care, sine x, divided by square root of x plus 1, whatever. This has less writing than the one, because we want to compute everything. So what the logarithmic differentiation, right, consists of? Well, first of all, you don't see any logs in here, which is a problem, right? So you will write this as a function, leave some space, because you have to put in the log. And you add logs to both sides. So technically, you make the problem worse, right? It did not have the log, and now you put in the log. So it looks like you made the problem worse, but essentially what you have done is you made this problem become a joke, because this ln in front is going to absolutely demolish all of the product rule, chain rule, quotient rules that you have in there, because you can use those formulas we learned before. See, ln y now becomes 4 ln x plus ln sine x minus 1/2 ln x plus 1. So those 3 formulas, I'm going to write them again. ln x times y is ln x plus ln y. That was used to break this product here into the addition of the two logs. Ln x over y was ln x minus ln y. That was used to break this quotient here into this minus sign. And finally, ln x to the power p, you kick p outside ln x. That was the one that kicked this 4 and this half exponent in front of ln x. These three formulas combined instantaneously killed all of the product rules, all of the quotient rules, all of the chain rules, and you just have the basic derivatives. When you take the derivative of this mess, on the left-hand side, you have 1 over y dy dx. Remember, you are taking the derivative of x in respect to y. Here is your implicit differentiation kicking in. On the right-hand side, you just have a joke after a joke. Copy 4, 1 over x, plus copy sine, derivative cosine on top. Copy half, derivative of ln, put function as is, the derivative on top. We need to ship this function to the other side. Remember how I copied the original problem in my derivative? If I define this problem as y and I have to move the y to the other side, there it is copied. So when I move my y on this side, all I have is 4 over x plus cotangent x minus 1 over 2 times x plus 1. And I just copy in the original problem for y, and you are recognizing this other part that came from breaking the formula apart through those pre-calculus formulas for logs. So dy dx is equal to the original problem, which was x to the 4 sine x divided by the square root of x plus 1, I believe. Yep. And then times 4 over x plus cotangent x minus 1 x plus 1. Oops. And that's it. There's a parenthesis here. This one's supposed to be... There we go. Is it factored? It is. It's factored. You cannot factor this anymore because they're all different. It's equal to 0, right? Ready for equal to 0 for chapter 4. And the craziest thing is that if you are able to break this in your head, each individual derivative with practice would start making sense. This one goes here, this one goes here, this one goes here, because the log derivatives are, after e to the x, the cheapest derivative you can have. You are copying the function on the bottom and you put its derivative on top. That's why I was able to solve that problem so easily, because I only have to keep track of one thing at a time. So let's see another example of this worked out. Say you have the derivative of x cubed plus 6x minus 1 to the 8th power divided by the cube root of secant x. I don't care. Like literally put anything down. It doesn't matter what you put. Literally. The only issue that you might have with is if you put e to the x, because e and ln they cancel, so the terms work out a little bit different. You don't take the derivatives of ln anymore. But once you get used to it, you know. So the only thing that can throw you off once you learn this is e to the x if it shows up anywhere. But then you don't need to use a sledgehammer when you have e to the x around, because e to the x is easy. Okay, so what do I have? If I am to break this into ln, I'm going to have 8 ln of the top minus 1/3 ln of the secant, right? So I know that I'm supposed to, for the answer, I'm supposed to copy the original function as is. So x cubed plus 6x minus 1 to the 8th, cube root of secant x, times that big part. And now what is the big part? The top will be 8 ln of the mess. So I see that this one is going to be my coefficient in front times copy the inside of this as is on the bottom, and then its derivative on top. You're done with that term. Minus, I see 1/3 is my, 1/3 is my, so why is minus? Because it's division, it's minus. And then it's 1/3 because it's a cube root. And then the bottom of ln would be secant x, and the derivative of secant is secant x tangent x. Derivative is done. Just need to simplify this. So I have my x cubed plus 6x minus 1 to the 8th, cube root of secant x. And now what do I have? I can factor out 3 on the top. So that's going to be 24x squared plus 2. This will never be able to simplify further. And on the other side over here, secant kills secant. So that's just tangent x over 3. Done. Done, done, done. Now, what are the mechanics? The mechanics are write this as y equals to this, put ln on both sides, use the formula to break every multiplication into addition, every division into subtraction, kick out all of the exponents as coefficients in front, right? So those are all the steps that go in between. When you practice those steps enough, let's say 5-6 hours of practice should do it. Those formulas for ln's will kick in so fast that you will be very, very quick. Now I need to talk about pitfalls, stuff that I see wrong on exams all the time. Let's start with a noob mistake. So this is the noob right here, noob mistake. When you have ln of, let's say, I'll put e to the x, x sine x. That's ln e to the x minus ln x. And then the student says, oh, that's a time, so I put plus. Hell no, it's a minus ln sine x. Because this e to the x is divided by x. That's a division. You better have a minus, and you do, right? Now, e to the x and sine x is also a division. You better have another minus. And then the student will say, but it's you know, it's multiplication, and you said multiplication is plus. Yeah, but when it's in the numerator, when you have it in denominator, it will, right? If you write this as ln e to the x minus ln of x times sine x, and now ln e to the x minus ln x plus, you have to put the parenthesis, ln sine x, and then that minus distributes, see that? So minus sine x, there we go. Maybe I should not put the noob here because this is correct. Yeah, I shouldn't use the noob. If I am to put the noob over here, then I keep this as a plus. So I'm erasing the noob because this is correct. This is correct. So don't make the noob mistake, right? All terms that are in denominator get the minus, because it's always, the top is always divided by the bottom. So if you have 10 of these different functions multiplied, it will be 10 terms with minus signs. All of them will have minuses, even though they do have a multiplication there. And you see mathematically why. That when you break it with the quotient formula to kill the quotient and make it into a subtraction, then the second term will get its plus, but then when the minus distributes on both of the terms, they all turn into minus. So that's a noob mistake number one. If you put the plus there, that immediately kills the problem. And the second mistake, and I'm not calling that one a noob, this one is a noob if you put the plus. But the second one is dealing with ln e to the x. See, ln and e to the x cancel down to x. So you will not be using the formula f prime over f, because you're just taking the derivative of x. So if you have any kind of e to the power of something, of whatever function, then this ln canceled with that e, and that term does not follow the rule copy the function as is on the bottom and take its derivative on top, because it's no longer ln. So if I am to solve this particular problem using logarithmic differentiation, say y equals e to the x over, what was it, x sine x, to use the logarithmic differentiation, the derivative is copy the original function still, and now in parentheses over here, you see this becomes 1, because this simplifies to x, and the derivative of x is 1, and then minus 1 over x, and then minus plus cotangent x, because, right, you put the sine on the bottom, the derivative of sine is cosine, and then cosine divided by sine is cotangent. So these two terms follow f prime over f because they are both ln terms. The first term is no longer ln term because ln killed e and is just an x term. So the derivative of x is 1. So if e to the x pops up in the calculation, that tends to, make a little problem where you have to like stop and think. But if there is no e to the x, it is always f prime over f. So let's compute one problem with logarithmic differentiation, maybe for the tangent line, if I can find any of the tangent lines. There is a horizontal tangency, there is a logistics growth is there, so you can understand the population stuff. Higher order derivatives is just gonna nest. I don't see any straightforward. Oh, there are tangent lines. Okay, good. Oh, nice. Nice. Find the tangent line to a function y equals x raised to the sine x at x equals 1. Oh, this is one nasty derivative. You have to use logarithmic differentiation here. And you actually have to write all of the steps. The shortcut will not work because you are going to actually get the product rule embedded later on. So far the problems, logarithmic differentiation kills all of the product rules. This is a new type of a creature we haven't had before. This is a function raised to a function. And that one is born for logarithmic differentiation. So Let's go. ln both sides. As soon as I ln both sides, you see that this sine x jumps in front and it creates a product rule. So we are able to break this f of x raised to g of x deal. We were able to break that by using ln. And all I used was ln x to the p is p ln x. And now this p was a function, sine x. So that's what I used. And I came up with this form. When I hit this now with the derivative in respect to x, we get good old 1 over y dy dx on the left. The derivative of ln y is 1 over y. And then I was taking the derivative of y in respect to x, so I have to follow with a chain. That's implicit differentiation, our last lecture. And on the right, I have a product rule. So we have to crank this product rule. That would be copy the first times derivative of the second plus copy the second times derivative of the first. Here's your dy dx. Copy original function. And now over here, sine x over x plus ln x cosine x. Yay! We have our derivative. They want this. Did I write it at x equals 1? Yep, I did. They want this computed at x equals 1. Fine, we can do that. Slope is my derivative computed at x equals 1. That will be 1 raised to the sine of 1 times sine of 1 divided by 1 plus ln of 1 times cosine of 1. Slope is 1 raised to the blah, whatever sine of 1 is just going to be a 1. Open parenthesis, sine of 1 divided by 1 is that. ln of 1 is 0. So the second term dies completely, and we just have sine of 1. So now I have my slope. Slope m is sine 1. By the way, this is a problem 59 from the book. So you are probably going to see similar stuff on your homework and exams. So we have the slope. Remember that the y was f computed at 1? Well, that's 1 to the sine of 1, which is a 1. So I have a slope, and I have a 1, 1 point. So y equal mx plus b, y is 1, m is sine of 1 times 1 plus b. So b is 1 minus sine of 1. And here's the tangent line. Tangent line is y equals sine of 1 times x plus 1 minus sine of 1. You could factor sine of 1 from the first two terms. It does help a little bit. You still have this plus 1 at the end, though. And there is the tangent line. Now, you might have a question. What is sine of 1? And for that, you need to use your calculator in radians and compute the value. on the unit circle, now this is a little review of pre-calc 2 with a trig. So on the unit circle, when you are dealing with these, let me just put the axes in. This point over here is 0. This point over here is pi over 2. This point over here is pi. Now that's about 3.14. About. Half of that is about 1.57, which means that the value of 1 would be somewhere over there. Value of 3 would be somewhere over here, right? Value of 2, whatever, somewhere there. These should be equally spaced, right? Here is your number 6 right here, right? So you can have 6, 2, 8 going back into this. So it is this angle. This angle here is angle of 1, and the sine is the relationship of this height over here divided by, now this is a unit circle, so this is also 1. So this height over here is calculated. Now, this is the arc length over here of 1. It's not a straight 1 value. So sine of 1, you can still compute it, but you have to make sure that you switch your calculator to radian mode. Because if you do sine of 1 degree, right, degree is 1/360th part of a circle. So 1 degree is this very, very, very tiny pizza slice on the bottom, which has nothing to do with our angle of sine of 1. So sine of 1 is a large value. I mean, you can convert it if you care, right? 1 radian converted into degrees. So these are your radians, and these are your degrees. And you know that pi radians has 180 degrees, so radian will cancel radian, and you literally need to divide 180 by 3.14, and you will have, if you care about, right? So it's going to be less than 60 degrees for the 1 radian, if you want to know what that measure is. So that's to understand just what the slope of sine x, of sine 1, sorry, slope of sine 1 is. It is the line that has this as a slope, sine of 1, which is a number. And you can also express that in degrees if you care. So let me quickly go in the calculator here and take a look at the, so 180 divided by pi gives me 57.3 degrees. 57.3 degrees. That is the angle of this tangent line, because that's its slope. And you have to shift it up and down by this amount. Well, that's it. I hope you are not disappointed with logarithmic differentiation. It is insanely powerful, insanely useful. And in the past, students says, well, can we just learn this and not worry about anything else, because this literally replaces everything we ever learned? The answer to that is, unfortunately, as I said, no, because later on in mathematics, you are going to use product rule to derive other formulas. You're going to see chain rule derivatives a lot. And it's, you don't use a sledgehammer to put the painting on a wall. So if you have to compute a problem that is just e to the x over x, right? You don't really want to use implicit differential. You can, but it's a simple quotient rule that you can quickly work on, or you're going to see this a lot. And, you do not bring a sledgehammer. Sledgehammer is going to do, all right? It is going to work. But there are these simple problems that you really don't have to bring the sledgehammer. So if you tune into my lectures for Calc 2 and Calc 3, even though this is something that I know for about 15 years, you know, this logarithmic differentiation, I still talk about these in a higher level courses because they tend to be a little bit faster on the cheaper problems, and you don't also have to worry about e to the x anomaly and, you know, a couple of those other things. So they're still useful.
Also, we did have to use the power rule in that last problem, even with the logarithmic differentiation.
Yes,
So
the
you still
product
need to
rule
know it.
was, yes, the product rule, you're correct. The product rule was used here. However, if you go to the second derivative and use the logarithmic differentiation, it will kill that product rule and make it into,
Yeah. Mhm.
right? So
Yeah.
with a higher order derivative, you can still avoid it. But again, you know, it becomes, you know, diminishing returns, right? Because then you have to worry about the second derivative and all of these kind of things. So if you go sufficiently high, you can always eliminate all of the product rules and quotient rules. But sometimes it's just, you know, you say, okay, fine, I did it once, and but that's a very good catch, and that's exactly correct. Very good. Any other questions, concerns? Would anyone like to express their amazement with logarithmic differentiation? And no,
That's really cool.
you're just all
Yeah,
dead
I'm really
inside.
So amazing.
Okay, here we go. I'm thinking, like, if this was not amazing to you, I mean, you are in the wrong field. I mean, this is something that is just, you know, it's just there. All right. So let's take 5. We'll be back at 12:50 for literally 10-15 minutes of inverse trig functions. We're not deriving any of that stuff. That's for the honors course, right? We're just going to write the formulas that you need to memorize, and that's it. So 10-15 minutes when we come back to finish it, and that will be it. So see you then. I have to go reset all the titles, and cooling is still okay, I guess. So see you in 5.